for flying the helicopter, we call it collective pitch, tail rotor pitch, and we call them as cyclic, because then it is split into longitudinal cyclic, lateral cyclic. But then when you give that these commands, basically what pilot does is he just moves the stick, and the effect of that motion of the stick to the rotor system is basically initially the rotor disc may be horizontal, and when he gives longitudinal, the disc may tilt with respect to the shaft. So, initially the disc is like this, then it tilts. As a result, it develops a forward component of the rotor lift force, and that will move the helicopter forward, but that will also give a moment about the CG, therefore, it will pitch. So, these two you cannot decouple. Similarly, you can do lateral, that means he tilting it this way, which implies he can fly in any 360 degree. Okay. This is very primitive way of explaining the helicopter controls, very simple way, but in reality all of them are coupled, because if you do one, in the sense if I want to climb up, very simple, but because of the increased lift, or we call it thrust, there will be a torque will increase. As a result, the helicopter will start turning. That means he has to control. Okay. Similarly, when you want to do longitudinal, because of the Coriolis, centrifugal, all those effects, the gyroscopic effect of the rotor, he will get the roll, which is undesirable, but you can't help it. That means he has to keep on adjusting. If he wants one, he will get an undesirable response, and he has to compensate for that. Okay. That is why helicopter flying is more difficult. So, first the pilot gets trained in fixed wing flying, all the helicopter pilots, they first go through flying in the fixed wing, then they come to helicopter training, but here the flying is different. So, they go through another training, and these pilots are then helicopter pilots, that is all, and they have to get the hang of how to fly, okay, because his hands, his legs, everything is engaged in the vehicle dynamics. Now, you see basic, and another thing is the helicopters are unstable both statically as well as dynamically. So, the pilot has to keep on, he has to fly. It is not that he can take his hands and legs off from the system and the vehicle will beautifully fly. No, it does not happen that way. Okay. So, he is in the loop to fly the helicopter. Suppose you say you do not want the pilot, like now you say autonomous, that means some other system should be inside to take care of the control. That is where automatic flight control systems, basically that is to relieve the load that is given to the pilot, okay, but those are expensive, then you increase the complexity. That is why in the design of a helicopter, usually if you design the vehicle, the basic vehicle without any of this closed loop controls, if the system behavior is very good, then the effort required to make it better is less. But if the basic system is not very good, then the effort required to fly by the pilot is more. That is why when I spoke to some pilots, he said our job is not just to fly the vehicle, because even though the pilot has to fly the vehicle, it is not that he has to only fly, because he has to do other tasks. Like other tasks means maybe reconnaissance, or if he is a attack helicopter, he has to operate certain other things. He will look through various other environment. That is why his workload is more. Whereas if he is always concentrating on flying, then he can't do the other work. So the developments of, see the, I would say the, in the helicopter field is towards these directions. How do you reduce the pilot workload? And then how do you reduce noise? How do you reduce vibration? How do you increase the capability of the helicopter? Okay, there are several directions, and the gap between theory and experiment, that is still there a big gap. What you measure and what you theoretically calculate, there is a gap, and how do you fill it up? That is where the research, all the research is going towards these directions. And with the technology improvement, can I replace some rotor blades with the metal rotor blades with composite materials? Okay, and the cockpits, you will have all sorts of meters. Now remove all those meters, have a glass cockpit, they say, just a simple display. Pilot can push whatever he wants, it will be displayed. So the technology improvement is in those directions, but still for the scientists there is a lot of problems. Enormous number of problems exist in helicopters, even from a research point of view. Okay. So you have learnt about these basic controls. Now I will give you a schematic of how these controls are. This requires a little explanation more. See, this is for this particular lever, we call it the collective. That is, when he moves, what is he really doing? Because you say we have given the pilot a stick on the left hand and a stick in the front and pedals for the leg. But when he moves, what really happens? What is that he is controlling? So that is by this diagram. I will briefly explain, because this is important when we go for the next stage. When the pilot moves this stick up, what he does is, through a mechanical, please understand, mechanical and hydraulic system today, there is something called a swash plate. Please note, this is a new terminology which you do not see in aircraft. Okay. Why? What is this? I will show a component which we have, because the pilot is sitting in the non-rotating frame. He is in a non-rotating frame. The blades are in the rotating frame. Okay. You have to transmit the control from non-rotating frame to the rotating frame, right. Now the control to the blade is simple, because we all know, we are all from aeronautics, we have only an aerofoil. What you can do at the most to an aerofoil, you change this angle, pitch angle of the blade you change, that is it, you have no other control. Now you may ask whether RPM is controlled. Okay. In big helicopters, RPM is regulated. Okay. You do not vary the RPM for flying. Okay. But pilot has some control over changing the RPM little bit, but he always keeps the RPM at a fixed value. That is by, like your motorcycle, through this he holds it and he can turn it. Okay. That means engine throttle increases a little bit, but he can't change it to any value he likes. It is only within a zone because you will have a meter that tells you what is the rotor RPM and what is the engine RPM. Please understand. Now you see in helicopters, whatever we are going to develop from now on in terms of the equations of motion or thrust, power, anything, rotor RPM is a fixed quantity. It is not a variable quantity. That is in helicopters. Okay. Now you imagine if you want to make a small, all this autonomous, that micro air vehicle, everything, there you may vary the RPM. See, the control may be through RPM control, but here RPM is fixed. What you have control is only the pitch angle, pitch input. Okay. Now, what that pitch input, because we have several blades on the rotor, from 2 and more. We will come to the rotor system later. When the pilot pulls up, what he does is, this is the swash plate mechanism. It has 2 components. One is a non-rotating, another one is a rotating, with some bearings in between. That is all. And that system, I do not know whether if I will show another picture, but it is like this. This is actually the swash plate. I do not know whether you can see, I do not know how do you put it. This is the what swash plate. You see, I can move the inner one. Okay. You see, the inner one can move and the outer one is fixed. From the outer, the control rods from the outer will go to the pilot, that is non-rotating, and from the inner it will go to the, I do not know whether you can, what, inner one goes to the blade. So, depending on how many blades you have, you will have a non-rotating, and rotating. Okay. This is to pilot, this is to blade. So, the swash plate mechanism has 2 parts, and schematically is another picture which I can show here. It will be like this. That is very simplistic, because please understand, this is a, see, as a mechanical system, this is a very beautiful thing, because people have thought about how to really design a mechanism through which you control from a non-rotating to a rotating system. Now, if you want to do some next step, this is a very heavy system, heavy mechanical weight, has a heavy weight. Suppose you say by electrical, some wireless means I control. Okay. If you do that, well, maybe that will become, after 50 years, that may become the trend. Okay. Because mechanical systems still are reliable. You follow? So, they still use it, swash plate, because if it goes, that is all, the vehicle is gone. So, these are all very critical systems of the helicopter, flight control systems. It should never fail, that is it. So, you see, this is the non-rotating, and this goes to pilot control, and above this is the rotating swash plate, rotating ring, and this is the control rod. Now, if I move this entire unit up or down, what I am doing is I move this control rod up or down. Not only this control rod, all the, if I have 4 blades, every blade will have its own control rod. Okay. I move everything simultaneously up or down. Okay. When I do simultaneously up or down, I change my, there is a pitch bearing. So, you see what happens, This if I move it, this is going to rotate about the pitch axis. So, all the blades will experience same change in pitch angle. I am not using the word angle of attack, I am only using pitch angle, please understand, because angle of attack we will learn later because it is too complicated. Pilot gives only pitch input. So, now let us write the pitch to the blade as theta 0. This is to any blade. K represents kth blade. We always use a subscript K to represent kth blade. Okay, you can say kth blade. I put a 0 to indicate that this is a collective pitch input. Okay. This is called collective. Collective pitch input pilot gives, which means he moves the stick up because his collective lever is up. This lever, this swash plate will go nicely up or down. Up, normally it goes up, depending on where this control rod is. It is in front or back. Please understand. I can have this rod in front of the blade or back of the blade, depending on I move it this way or I pull it. Basically, he moves up and down is collective. If he moves it up, pitch angle of all the blades in the rotor system change simultaneously. Okay. There is no difference. All the blades will experience same pitch change. Now, let us go to this stick. This is this control stick for cyclic. This is the cyclic stick. Okay. I want, if we move forward, okay, there is a lot more inside of this. Vehicle will fly forward. Please understand. That's all. How the swash plate will move, I will say there is some rigging done. At present we will not bother about the rigging. What it does is swash plate will, instead of moving up, it will tilt. It will tilt in the sense the swash plate, instead of up, it will tilt like this. Okay. You can now tilt it any plane, please understand, right. Let us assume it is tilted about some axis and it is tilted like this. Okay. Now, as the blade goes round and round, what happens? This control rod keeps going up and down. Okay. And when it goes up and down, it goes up and down in one cycle. So, we call it 1 per revolution. Okay. What happens? The pitch angle changes once in a revolution. Okay. Now, you can tilt it in this, about this axis, or you can tilt it about this axis. Okay, swash plate. So, these are the two axis tilt you can do. Now, if you tilt in these two planes independently, which means by suitable adjustment I can tilt along any axis, you follow, because if I can tilt in this axis, if I can tilt about this axis, that means I can suitably combine, I can tilt like this, I can tilt like this, that means this is, I can go in this fashion, any fashion. So, that is called cyclic pitch input, and it varies once in a revolution depending on where the blade is, because if you say I tilt like this, if the control rod is here, there is no change, because whereas if my control rod is here, if I tilt, it goes down and the control rod at the back goes up. So, depending on the location of the basically control rod, but we do not write control rod in pitch angle, we write it like this. Okay. Now, I will represent what is psi k. You take this as your rotor disc, and this is the standard reference. This is to the tail. You are viewing the rotor disc from top. Okay. This is my rotor omega, and the rotor blade can be in this is called psi, but if it is a kth first blade, this is psi 1. If it is a second blade, you will have right like that. So, kth blade, it will be psi k, that is why I put psi k. Okay. The azimuth location of the blade. Okay. Now, please understand, we do not represent the azimuth location of the control rod. Okay. Control rod may be in some other location, because of this tomorrow when you come to the lab I will show you, but we represent mathematically, hey, my pitch angle varies cyclically. These two are cyclic inputs. So, you have collective, okay. I call them cyclic. I am not now assigning whether it is a longitudinal cyclic or lateral cyclic. Please understand, then that requires dynamics. What you call it as longitudinal, what you call it as lateral, you have to know a little bit more about the dynamics. Right now, they are called cyclic inputs, and K represents the azimuth of the kth blade. Okay. So, now if you have, that is why this is written psi, this is the first blade. If you say two pi over n, n is the number of blades in the rotor system, number of blades. Okay. Because if it is the first blade, this is 0, psi k, psi 1 is psi, that is this. If there are 2 blades, this will be pi, so you add 90. If 3 blades, it will be 120, 4 blades 90 degree. Okay. So, this is the general expression for the location of the kth blade azimuth, and this is the psi is what? That is the angle of the first blade, but that is nothing but omega t, right. Omega is the rotor angular velocity. Got it? Now, you have only these 3 inputs pilot gives. Now, please understand, this is the input to main rotor, sorry, because I am now restricting this to one main rotor, one tail rotor system. Okay. Now, you please imagine, if you have a 2 contra-rotating rotors, there is no tail rotor. If you have one rotor in front, one at the back, that is tandem. There is no tail rotor. Only thing is, one is a main rotor, another one is also looks like a main rotor, both are horizontal rotors. Now the controls, as far as the aircraft is concerned, in the helicopter field, this is what, it is not that when you have two rotors, pilot may give collective, pilot may give cyclic to both, but he will have only this control. Okay. Now you imagine for a, that is why mechanically simple is the single main rotor, single tail rotor, because tail rotor, the pilot puts the pedal, he will have a pedal here, he will somewhere, and he will act, and that goes to the tail rotor, and tail rotor you have only collective. So, please note tail rotor only collective. So, we call it theta 0 tail rotor. Now, you see 4 controls. This is for a single main rotor, single tail rotor, 3 for main rotor, 1 for tail rotor. Now, if you have, hey, I am not going to be like this, I want to build two rotors, let us say contra rotating, one above the other. One above the other if I do, then it is a little tricky. You can't represent it in this, because there is no tail rotor. Okay. Then you always talk about what motion you want. If you want to climb up, you give collective. Okay. If you want to fly forward or sideward, you give cyclic. But if you want to turn your heading, then you give yaw, that is all. That you may do by a differential mechanism between the two rotors. Okay. Because if one rotor produces a little less torque than the other rotor, because they are all contra rotating, please understand, both do not rotate in the same direction when you have two rotors, whether it is a contra rotating one below the other, or it is side by side or one behind the other. Okay. Now, you imagine I say, hey, what are the controls I have to give to generate motion of the helicopter? Collective you give, then when you give collective, both the rotors collective pitch will increase simultaneously. Okay. So, you will go up. When you want forward, you say cyclic, you can generate by differential collective, because if one goes up, another comes down, then you will go. Okay. That is where the control rigging, all the control mechanism becomes different. Okay. Whereas, if you want to yaw means I change my heading. In the case of a single tail rotor, very simple thing, okay, change the pitch angle of the tail rotor so that I increase or decrease my force. So, as a result I will yaw. Okay. Very simplistically. Now, imagine if you have different types of rotor system, in the sense rotor configurations, helicopter configurations, not rotor, whether it is a contra rotating, one main rotor, one tail rotor, or whether you have tandem configuration or side by side configuration. Please understand the mechanical linkages in those cases, all the transmission becomes complex. Okay. That becomes a little difficult. I want you to read that how they control those helicopters configurations. Ultimately, you have to do this. You find they are more complex systems. Okay. So, that is why mechanically simple is single main rotor, single tail rotor. Now, you understand why most of the people, those who have the expertise in manufacturing a particular helicopter configuration, they stick to that. Because today, of course, Boeing makes tandem, okay, that is CH Chinook, and only they make. It's not that every other fellow starts making it. Similarly, that contra rotating, the Russians, Kamov helicopter, they have experience, and they make. Of course, US now wants to call the same thing by a different concept. This is just is all they call it A, B, C. Okay, advancing blade concept. There is nothing fancy except the ABC you call it. Okay, advancing blade, because just last week I think I saw, because this was this particular thing, it is a contra rotating rotor system, that is all, there is nothing. Only thing is sometimes it is fancy to call a new name, so that people will, oh, what is that, okay. Otherwise there is nothing special. US started this long time back, Sikorsky, but of course they had a lot of problems, because they thought as we go along the program we will learn the advantage of something. They thought I can get the advantage from both the rotors, but actually the disadvantage also comes from both the rotors. So, what they thought they could achieve, they could not achieve, okay, and the project was abandoned. But again I saw just about last week in newspaper, oh, they made this helicopter again, maybe they are again trying to do it, okay. But they call it advancing blade concept, but it is nothing but contra rotating rotors, which the Russian Kamov has. But only see, that is why the technology and the knowledge, once you gain in a particular configuration of a helicopter, please understand, particular configuration of a helicopter, the industry does not want to lose it, because you have an advantage in manufacturing and you know what problems you will face, and you have addressed the problems, you have solved the problems. Even I will give you just a little story, but it is not a story, it is a reality. There was a contract for building that, I think it was Apache at the time, if I am right. So, that was initially Bell helicopter also tried for that, but Bell has been manufacturing two bladed rotors, okay, initially. So, when the demand for increased weight and other things started coming up, they said they again gave two bladed, but then when the attack version, there were some advantages, so it went to four bladed, because they did not have, then only they started making four bladed helicopters, okay. So, you lose a big contract itself if you are not experienced in a particular configuration. Of course, each industry has its own speciality, because apart from theoretical knowledge, the practical knowledge of implementing, manufacturing, proving is much more tougher, because any new rotor configuration, please understand, it takes more than 10 years. When they wanted to change a metal blade to composite blade, metal blade to only blade change, everything else is same. They said I will replace in the helicopter, current helicopter, whatever is a metal blade, I will remove it, put a composite blade. That alone took 10 years, please understand, just replacement of a blade, because the complexities, the whole dynamics, the structure, the aeroelastic, all the problems, you have to, now it is a new set of problems, okay. So, even today there is one small article says, still people do not know. They changed some metal to composite, identical, dynamically it is, dynamically means frequencies, everything is same. But then when they put that rotor, you have a higher vibration. They said still we do not know, that is all the question is. Finally, we do not know why. Okay. So, these things happen, I change something, you think everything is identical, but then when you put there, the measurement shows it has a higher vibratory levels. And that because he was a industry person who was that Prouty, which I showed one of the books, he writes small articles on what do you call, that is a magazine which is called Vertiflight. Okay. It is the American Helicopter Society, that is a journal, this is a magazine. In that small without equation one article will always come. It's a very interesting articles. He says we still do not know why. So, there are many unknown things. Okay. So, in this course we will stick to one main rotor, one tail rotor configuration. Okay. And now you know the input. Input is collective and cyclic. So, 3 inputs go to the pilot and to the main rotor, 1 input goes to the tail rotor. That is all for helicopter controls. There is nothing more, pilot gives only these 4. Okay. And now I will briefly go to the rotor systems. It is a rotor system. What do we want? We have a blade, we need to attach it to the hub and then the blade should rotate, that is all. How do I attach it? That is a very simple question. And the type of attachment determines the type of rotor configuration. Okay. When I was telling you the history last class, we said that Sierra put a flap hinge, that means he delivered, it was an engineering solution for a problem. So, he introduced a physical flap hinge, and what we need is, now you know that there is a hinge, we also need to change the pitch angle. That means, if I rigidly attach to the hub, I cannot change the pitch angle. That means, I should have a pitch bearing. Okay. Now, you see, I should have a pitch bearing which will change the pitch angle of the blade. Now, you need these 2. You must attach it, pitch bearing should be there, but you can have a hinge, you may say. So, now let us look at, now you know what you require. This is called a seesaw or teetering. This is always for a 2-bladed rotor system. But tomorrow what we are going to see, which is a 2-bladed helicopter model, that is not this system. Okay. That is a little different. This is 2-bladed is seesaw. What is happening is, one blade here, another blade here, it is one unit. You come and hinge it at the center. So, hinge is, it is like a seesaw. If one blade goes up, other blade goes down. Do not think about operating another, just normal. I have put a hinge here, you see, this is the attachment, this is the rotor shaft. Okay. I put a cup and then attached it, and I have a pitch bearing. Please understand, I have a pitch bearing. Pitch bearing is always required. Yeah, otherwise I cannot change the pitch angle of the blade. Okay. Is it clear? Now, this is called the seesaw or teetering rotor. They have only the this flap hinge, because the blade can go like this, that is all. So, I have only a flap hinge which is located at the center of the hub, please understand. Okay, you look at it, the flap hinge is right at the center. This is the seesaw, two bladed, this is only for two bladed, please understand, this is two bladed, four bladed they do not make like this. Now, you go, this is another rotor system which is called the fully articulated rotor system. Okay. In this you need to have a pitch bearing, so that is here, that is what this arrow, that semicircular arrow represents, I can change the pitch angle. Then I have two physical hinges, please, there are two physical hinge, one hinge is this, that is flap. Okay. Another physical hinge is here, that is lead lag. So, you have two hinges, one bearing. Then you may ask, what happened to the lead lag here? There is no hinge for that. Okay. Two bladed rotor system, they do not put it. Then you will say what they will do, that design part later, because it is little bit more you have to know to see why they make it like that. Okay. Because it is there is a lot of dynamics involved in that, why you make certain decision the way. This you will understand as we go along, you will say, oh, this is the reason, this is the reason, this is the reason, this is it. Now, the interesting part is these hinges are not at the hub center, please understand, they are not at the hub center, they are away from the center of the hub. So, there is a offset. So, you call it a hinge offset. Okay. That is, you have a, this is like this, you put a hinge and the blade goes. So, this distance we call it, please, the symbol I am using is the same throughout the course. I will not change, today I write one symbol and tomorrow another symbol for the same quantity. Okay. Is hinge offset. Okay. Now, this is for flap motion. Flap is, that is why I plotted, this is the plane of rotation and the blade is can go like this. Okay. And I have put deliberately the offset here, because physically I cannot put, when I have 4 blades I can't do it, or 4 or 3 blades, because you have to attach them, you need some geometry, you have to have some space. So, it is tilted. This is called fully articulated rotor system. All the blades, all the helicopters were built like this. Even the attack helicopters, you go to Russian helicopters, everything till 80s, but of course, some slight change will be there, are like this. Okay. But now, you know that when you have a physical hinge, the blade is going up and down, what will happen? You have a wear and tear problems. Okay. Maintenance, number of parts, everything is high. So, now you see, it is from a operational point of view, you find that articulated rotor systems are good, I can attach them everything, but maintenance is, you have to replace parts. Replace part means you have to bring down the whole unit and then remove it, put it, then only make it operational. So, from design point of view, number of parts, you have to lubricate several places. I will show later one picture, then you will get an idea. Said, hey, we should remove the hinges. That was a, everybody will say, why do you put an hinge? I remove a hinge. That means I take the blade, simply bolt it. It's good. But then that is what the hingeless. That means there is no hinge, right? I said it easily. Just take the blade, bolt it. Okay. It's easily said than done, because if I attach it, I must allow flap motion of the blade for flying. Because what do I do? When I have the rotor like this, if I want to fly forward, I am tilting the rotor disc. How do I tilt the rotor disc? The shaft is straight, please understand. Earlier I told the shaft is always straight, but the rotor disc is tilted. That means when the blade comes here, it goes up. When it comes to the front, it is down. That means I want the blade to go up and down in a prescribed way. That means I want flap motion. Flap is completely restricted, like a propeller. You have a propeller blade is there in aircraft. It is very rigid, you attach it, bolt it. Then you have, this is rotating. If you want to fly forward, what? It will not do this. You have to tilt the entire shaft. In helicopter, the shaft is not tilted, only the rotor disc is tilted. That means rotor disc tilt happens because of flapping motion of the blade. So, the flap dynamics, now you understand flap dynamics means the motion of the blade in out of plane of rotation is important. Only by controlling that the helicopter is flying. Okay. Now you say I make it hingeless. Hinge is kept to relieve the moment, because he said that if I have a movement, I don't want movement, but I want the motion. Moment should be, that is a good solution. But then this has its problem. Now you come here, you don't have anything, but of course pitch is there, pitch bearing is required. But how you design, that is why I said when the technology for manufacturing changed from metal to composite, okay, please understand, metal to composite, when it changed, then only the realization of a hingeless blade became possible, because by putting layers of the composite cloth, you may call it, or pre-pegged, you can adjust the stiffness of the this particular region. I call it this region, please understand this region. What I do is, I don't put a hinge, but I will deliberately make it flexible there. The blade is made to be flexible at some zone, okay, and it is a virtual hinge, okay. This is like a, you want to be the blade to behave like this, but there is no hinge, you follow. That means the manufacturing, you have to, how do you design the blade such that there is a flexibility at the near the root, because this is the root section near the root, but it should have sufficient strength also, because centrifugal force is pulling, okay. So, the strength and the flexibility, the stiffness. So, by tailoring, by adjusting the layup, they manufacture. Today, of course, this is quite common, very common, hingeless rotor blades, main rotor, please understand, now I am saying main rotor blades. even Indian, that advanced light helicopter, that is this composite. Now you see, once this was first started in Germany, okay. They made this helicopter with a composite. Actually, no company would like to be left behind in technology, okay. So, because they see the potential. Of course, composites has its own problems, its own advantages. We will not get into all those issues, because if you go, that will be another story of its own, okay. What we say is, with the technology development in composites, the realization of a hingeless blade was made possible, and today companies make hingeless blades. ALH blade is a hingeless, that is advanced Indian helicopter blade, that is a hingeless composite rotor blade. That means the manufacturing technology you have to know, the design technology, the design, everything you must know. That is why today this is common, composite rotor blades. But still you have a, now you see, you have simplified the rotor system by removing the hinges, but still you have a pitch bearing. Pitch bearing is also a bearing. Now can we remove that? Okay. That is the next level of rotor system, which is called the bearingless rotor system. Okay. I remove that bearing also. You got it? Now when I remove the bearing, then how do I change the pitch? Okay. This is a very, very primitive schematic. I have a, this is called a flex beam, okay. This is called a flex beam, okay, which is a flexible beam. In torsion, it should be flexible. In bending also. Bending means what? Please understand, this blade can bend this way, this blade can bend this way, lead lag, and it should be flexible in torsion, okay. And that was made 80s. Of course, the concept, people at even 1960s, please understand, I can have a concept, but then to make it a reality, it may take 50 years. Maybe you would have written something and that is all, but somebody else will keep on working. Now this is the flex beam, and then I will show another picture, which is a, today they manufacture these blades, but only tail rotor blades, okay. Tail rotor blades are this. Main rotor blade, still this is what is used. This is only one helicopter is tested, only one helicopter, a lot of complexities, okay. There is a German, I think, what is it, EZ-135 or some helicopter, I don't know the number you leave. They manufactured, they flight tested a few years back or earlier, they were flying there. Because now you see, I have made the rotor system simple, but the dynamics, the manufacturing, all other problems. So maintenance people, it is easy, but they say it is a nightmare for the designer, because designers do not understand many things. Please understand, you may say, I want to do it, I will put the new things and then it will work. Industry has to mature to take that concept, and then say they will not immediately buy it, because in practical implementation some concepts may not even be realizable with today's technology or the knowledge. So one may have to wait for another 50 years to again start, okay. But these are the rotor configuration. Sometimes people may call it this rotor as a rigid rotor, rigid, but it is not really rigid, it is just for some reference, but I would not call any rotor as a rigid rotor, because all rotors are flexible, okay. So for clarity of distinction, you call them as articulated, hingeless, bearingless. Is it clear? Now I will just show the real helicopter hub to the schematic. Okay. So that you will have an idea, this is a articulated rotor hub, actual helicopter, more than 450 parts and about 20 lubrication points. This is the schematic for that. Okay. Then hingeless rotor, much it looks cleaner, okay, and simpler. It looks simpler, but the designer, it's a nightmare. It is much difficult, because later we will come to that. This is much simpler, and this has 150 parts and maybe one lubrication. Lubrication is basically they put some damper. We will go to that later. Okay. To this is the hingeless. I will explain briefly. See, there is a collar. Okay. The blade is here. This is the flex beam, which is a composite material. What you do is you twist this beam by pull the lever up and down. This is connected to this outer sleeve. So, there is a sleeve. What you do is, this is the inner flex beam which is bolted to the hub. This is like a sleeve. The sleeve goes and joins. So, it will be like this. If you look at it, and here you have a, that beam will be going. This will come and join. Okay. This is the outer, this is called the torque tube. Okay. This is called the flex beam, and this is the blade. Now, what you do is, you have a lever attached to this, you move the lever up and down. That means this will twist. When it twists, it will twist at this end of this flex beam, and then the blade pitch angle will change. But now this is a several path, load path. The blade has one control rod, this is the path, that is what will always be there, and this is the flex beam. Okay. And this should be, it should take the centrifugal load, it is flexible enough to flap, lead lag and twist. So, manufacturing is much tougher, because you have to know the dynamics and then properly design the entire section. Now, you see, this has the number of parts, it is less than 50, and there is no lubrication for this. So, you see the complexity of articulated in the mechanical side to the very compact, clean system of the bearingless. Now, all these things took several years, actually several decades. Okay. Now, you will find, if a company is experienced in manufacturing this, they will stick to it, because it is not easy from here to here. Okay. This may again require 10-15 years of developmental work and testing work to replace. Okay. That is why they will not, okay, oh, everybody is making, let us also make. No, it is not like that. That means it is your lifetime. Please understand, in aerospace technology, it is a lifetime of an individual to concentrate working on that to achieve. When you start at 25, you will say, this is what I want. Maybe when you are 50, you may realize, oh, that is what now I have made. Okay. It is the, that period is very long. It is not like every 6 months I will have a new design coming up, new product. No. Okay. It may be a generation before a new product comes, there may not be any new product. only improvements in the technology that changes. So, this is how the whole thing went. Okay, yeah. Any? No, there is a fatigue damage. See, fatigue, that is always there. Yeah, suppose you say hingeless blade, you want it to flap up and down, right? That means what? You are actually, suppose you take a pin, you want to break it, what do you do? You keep doing like this, and then it will break. That is a fatigue. Here, fatigue is very important, but you don't want the blade to break, which means what? You have to design such that the fatigue life is what is mandated, what is required. Okay, because I don't know what 5,000 hours, the blade requirement 5,000 hours of the blade, okay, life. After that, throw it. Every component may have some life, throw it out. Because I was reading some material now, that is a very interesting thing. The pitch link rod, what we showed, that pitch link, this rod, the rod which goes from blade to the hub, that gets all the load. The pitching moment comes as a axial load on that member. Now you can make it very bulky, heavy, so that you will give infinite life, but they don't want infinite life. So what you do is you reduce the weight, but life also goes down. You say so many, after that remove it. Now in the Indian Air Force, this is one of the main things. You know, we operate Russian helicopters, plenty. Air Force operates. They all have metal blades, and there is a life. After that, the blade has to be removed. The blade looks beautiful. There is no visible damage, nothing. Everything is wonderful, but the blade has to be removed because the 2 new blades have to be procured. I think the 2 new blades, what is it? It is 75 lakhs. Okay. Now I don't know, ALH blade, each blade is 1 crore or pair is 1 crore. It's about a crore. Okay. Now Air Force was saying we have to keep on import. They have lots of blades. So the whole question is, can you tell us that I can operate at least another 10% of the life which was given? The manufacturer of the blade will say no, because he can sell more blades, right? But the operator will always say, hey, you know, I want to extract as much as possible, but without endangering, because if anything happens, he will only blame the operator. He will say that, see, I told you don't operate, but you operated. Now what is the scientific way of improving? Because those blades were not manufactured by us. Okay. Now there is a program which is called life extension. So they did lot of tests, they have given some extension of 10% life or something like that. So these are problems. That is why all these things, they say 5,000 hours. See, I will not give you some of the things which are actually, whatever little I know from the industry thing. Something maybe it's good. Actually as students, it's fantastic to know, hey man, this is all really amazing. Okay, there are problems, lot of problems. So on one hand, somebody will say, I buy, it is like your bicycle, you buy your bicycle, you know, my father had, even it came to me. But aircraft is not like that. They will say you use it, after that throw. 5,000 hours. 5,000 hours means whether it is 5,000 hours of operation, or they will also specify calendar year. After that you throw. Suppose if you don't use it also, you throw it. Okay. These were the money. Okay. Now you know that if you make a flying vehicle, actually you dictate the economy to a large extent in that sector, because it is all high cost items. Nobody will tell you how they make. They will say we have put all our money, effort, everything to come to this. That is why I said to come to this blade, composite blade, the company took 10 years. Okay. 10 years means they are not going to come and tell you easily. They will, if they tell, they will charge you a lot of money. Okay, enormous amount of money they will charge. So these are the reality. But what we learn in this course is, of course, some practical things, interesting aspects, because that is to give you some, what is that, interest to the course. Otherwise, the mathematics involved is really terrible in helicopters. Nobody would like to work in helicopters, because equations are very, very long. Very long means one term may run to 30 pages. Then you will say, what, are you sure you are deriving it right? No, because that is the first question will come. If you write, keep on writing, what is that? Is it right or wrong? Right or wrong determines only finally when somebody does an experiment, you say, okay, is it close? That is what, and that is the reality. Okay, you will learn, you will see. But what I will introduce here is very, very at a low level. Now, there are some interesting points in the helicopter thing. There are several interesting things. One of them I just want to show. This is something which normally does not happen in aircraft. That is why I am putting this. This is the rotor disc. Okay. If it is in hover, hover means the helicopter is stationary, wind is not blowing, you are just above. Omega r is the velocity of the blade, and that is equivalent to relative air is omega r at any section. It is coming radially, that is normal to the leading edge, you can say. But the moment helicopter starts flying forward, that is here, what happens is, this is the forward speed of the helicopter. Please understand, that is nothing to do with the rotational speed of the rotor. Rotational speed of the rotor, so we divide this whole region into two parts. We will get to the math later, right now only explanation I am giving. Just what happens is, on this half where it is rotating, it is going into the air, the relative air is actually increased. But please understand, it is not that, because it is going at different azimuth locations. This V has a fixed direction. Omega r, as depending on the azimuth location, velocity is different. But when you go to this half of this rotor disc, actually this is called, you divide the disc into two parts. If this is omega, this is V, you call it advancing side. Okay, we will do this again when we do. Okay, this is called retreating side. Okay, advancing side, retreating side, it is two half. But in the retreating side, what happens? The blade looks like this, please understand. Okay, this is the leading edge, this is the trailing edge, this is the velocity V coming, okay, and this is my omega r. Okay. Now, if V is greater than the omega r, that means the flow is coming from trailing edge to the leading edge. Okay. And this happens in a region, and that region depends on what speed you are flying. We will derive that in the course later, how to get this. Okay. It's a very simple geometry, there is nothing more. And this region is called the reverse flow region. That means the flow is coming from the trailing edge to the leading edge. Okay. Whereas in aircraft, there is nothing like flow is from the trailing edge to the leading edge. Always it is from leading edge, trailing edge. Now, that is why in aerofoils for helicopters, when they get the CL, CD, CM, actually they go through full they will plot that CL versus alpha, alpha going to 360 degrees. That means you do one full loop, that means flow can come in any direction, okay. And of course, earlier you can neglect it, in the sense, okay, there is a, because there is a hub, you have to know what is the size of the region. These things we will learn later, okay. And some, they may not be very effective sometimes. And you have to know the aerofoil characteristic, in the sense in terms of CL, CD, etc., when the flow is coming from trailing edge to the leading edge. That means you have to do an internal test. But these are all lot of aerodynamic characteristics of the aerofoil, they are required when you are actually making the blade. But when we use it, when we actually design most of our analysis, many things, okay, we still take the 2D leading edge to trailing edge only. But the approximation we may make, we may neglect that region. Sometimes we may take the only the drag effect, or lift, you put it opposite, you do anything. These are all left to your own ingenuity, okay. But they restrict the maximum speed the helicopter can fly. But this is not the only reason, please understand, this is one of the reasons, because there are several reasons which restrict the maximum speed a helicopter can achieve. Because there is only one helicopter which went, I think, 400 kilometers or something like that, that is all, that is the maximum speed it has gone, that is only as a record. Otherwise, most of them fly around 250, 280, 280 is a very high speed, okay, 280 kilometers per hour, that is a high speed, all right. But one went around 400 something, because what will happen is this region, if you keep on increasing V, what will happen, this omega, this region is going to become bigger and bigger and bigger, and this side will become ineffective, okay. That is why when, now I am going a little off. When you study helicopters, there is, you can't say I fly at any speed, okay. There is a non-dimensional number you will learn, it is only below this you can fly. But if you want to analyze theoretically, you can take that non-dimensional any value, but it has no meaning as far as the helicopter as a vehicle is concerned. That is why sometimes even your research, as a parametric study, you can always say I will vary this parameter from 1 to 2 to 3 to 4, anything. But in reality, in the helicopters, even because there are some equations which I will introduce you later. It is an interesting equation, because which you will not come across normally in your course, okay. Just the flap dynamics in forward flight, that is the equation. And you will find for curiosity, you can change the forward speed to any value, just to see how the solution looks, okay. How the flap, not the how the helicopter blade flaps, how the equation gives a solution, okay. That is interesting. But in reality, you do not go to that region, because if you say, when you write an article or anything, you say, oh, this is useful for helicopters. No, it is not useful for helicopters, because I know some professors say, what is he talking about? He is talking some rubbish. What value he is taking? Because that value is meaningless as far as the helicopters are concerned, okay. So we will also in this course define some, and they say what range the real helicopters operate, because that is very, very important. Because it is not that any value you can take and then start putting it. Aircraft you can say subsonic, transonic, supersonic, all hypersonic, you can take anything. Here no, okay. There is no supersonic, but transonic some regions are there, that is in the blade. Maybe some sonic will come, but the helicopter will not fly at supersonic speed or anything like that. If you want to make, then you have to think how to make, that is a different issue, okay. So our speeds are highly restricted, right. So please note that we do not fly at any speed, there is a restriction.